So today we will be focusing on shared memory and what we call the bounded buffer problem. And this is very closely related to assignment number 1. So basically after today's lecture we'll have all the material we need for assignment number 1, which has already been posted on campus. The last thing that we talked about last time was shared memory and how shared memory differs from message passing. So today we will talk more about how shared memory is implemented. We will talk about the POSIX APIs for shared memory, how to create a shared memory object using the POSIX API, because that's what we will be doing in the assignment. But before that, let's discuss let's explain the bounded buffer problem, or the producer-consumer bounded buffer problem. So we have a producer and a consumer, two processes. A process that produces some data and the process that consumes the data. In our assignment, the producer will just generate some random numbers. And how many random numbers? That's going to be a command line argument to the program. Now the buffer, the producer and the consumer will be communicating through a buffer. That buffer could be bounded or unbounded. Now if the buffer is unbounded, we don't have the problem is very easy. All right? If the buffer is unbounded, then the problem is easy in the sense that the producer will never have to wait. There is always room for the producer, room in the buffer for the producer to write. Now, if the buffer is bounded, and the producer must wait when the buffer is full. So this is the point. We have a bounded buffer, then the producer must wait when the buffer is full. So now what's the point in using a bounded buffer? If you are designing an application with a producer-consumer scenario, why would you make the buffer bounded? Yes?
To keep your app from just using up all the resources on a computer?
Right, so you want to limit the resources, the amount of memory that you are using. And why is a bounded buffer usually sufficient? Why will it be sufficient? Why don't we need an unbounded buffer? In many cases, unbounded buffer is not necessary. Like if you are like in assignment number 1, there is a shared memory buffer, and the producer is producing some numbers. And the consumer is reading them. So why is a bounded buffer sufficient in this case?
Consumer will release the space or producer to produce.
Yeah, so it's the point here is that when the consumer reads an item, we no longer need this space. We can reuse it to put more items. So this is the idea. The idea is reusing a bounded buffer. If we are going to generate 1,000 items, we don't need a buffer that can fit 1,000 items. A buffer that can fit 10 items may be enough, because the producer is producing and the consumer is running concurrently and it's consuming the items as they are produced. And then whenever an item is consumed by the consumer, we can just reuse this space. So this is the point. It's just space efficiency. Okay, so now we will look into a bounded buffer solution that does not fill the buffer completely. So if the buffer size equals n, then the solution that we are about to describe only fills n minus 1, or only, it can never fill all n cells in the buffer. Why? So this will not make sense until we get to chapter 5 and attempt to develop a solution that fills the buffer completely, and then you will be facing some challenges. So it will not become clear why we are doing n minus 1 now until we get to chapter 5 and attempt to do n to fill the buffer completely and see what the challenges that we will be facing. So for now, just accept it that our solution will fill in n minus 1. If the buffer is 10, if the buffer can fit 10 items, we will only fill 9 items. When we have 9 items in the buffer, we consider it full. Okay. So let's take an example. So this is our buffer. Let's assume that the size is 3. So let's assume that the size equals 3, 0, 1, 2. And we will have 2 indices. Index n, which is the index of the next item to produce. Index of next item to produce. And out is the index of next item to consume. Initially, n equals out equals 0. So initially we have this. N equals out equals 0. N equals out equals 0. Now suppose now the producer produces an item of value 8. Then we will have this. So now we will have 8 is here. Now when the producer produces something, will this change the index or the out index? So in is the index of the next item to produce, out is the index of the next item to consume. When the producer produces something, which of these 2 indices should we advance?
En.
In. So now our n is going to be here. N is going to be the 1, and our out is still 0, because in terms of production, we haven't produced anything yet. So we have produced something, but we haven't consumed anything. So we are advancing the in, but out is still at 0. Then what if we produce one more item? Produce, let's say, a value of 4. Then we will have this. Out is still 0. This is 1, and in is now 2. Our in is now 2. So whenever the producer produces something, it's going to advance the in index. Okay? Now, what if the... Now, according to our definition of fullness, the buffer is full at this point. So the buffer is full. Because we have filled 2 out of 3. Then what if the consumer consumes an item? Consumer consumes. So the consumer does not take a parameter, because it will always consume the item at index out. So whatever item we have at index out, that's going to be the item to get consumed. So this will make it, so change it to, this is 0, this is 1. Now out equals 1, and in equals 2, and 8 is no longer there. So we'll assume that when an item is there, when an item has been consumed, it will no longer be in the buffer. So logically, it will not be there. Of course, in a real system, like in your assignment, the value will still be there, right? So it will be there until we override it in actual memory. But logically, it's invalid. There is no item in there, logically. Physically, it will be there until we override. Okay. So now, what will happen if we produce the next item? So what if we produce, say, 7? If we produce 7, one more item, we'll have this. 0, 1, 2, and this is 4, this is 7. Now where will our in be and where will our out? So our out is not going to change. Out is changed by the consumer, in is changed by the producer. So where will in go now? 0. It will wrap around to 0. Because this is where will the next production take place. So the observation here is that when we are incrementing these indices, when an index reaches the end of the buffer, the last index, in the next step, it's going to wrap around to 0. Okay, so now in is 0. So when we increment these indices, we're going to increment them in a circular manner by doing something like this. In equals n plus 1 mod buffer size. Okay. This is how we will, and same for out. They will both be incremented in a circular manner using the mod operation. Then what will happen if we consume? If we consume, we will get this. 0, 1, 2. Then we will consume the 4. We are left with the 7. So our out is now this. And our in is this. And if we produce again, if we produce, say, 19, then 19 is going to be here. Then we have the 7. Maybe I should. Producing 19 is going to do this. 19 is here, 7 is here, and this is 0, 1, 2. Now, again, production doesn't change out, so out will stay here. But it advances in, so our in is now this. Okay? All right, so this is how it works. Now we know that it's full here, and this is full. And this is full. So we have in these 3 cases, the buffer is full. Now, in the code that we will be writing to implement this, the consumer will wait when the buffer is empty. So the condition for empty is obvious, in equals out. So condition for empty, condition for empty is in equals out. Now what's the condition for full? What's the relation between in and out when the buffer is full? So look at these 3 cases and generalize. Can you come up with a general mathematical relation between in and out when the buffer is full.
In plus 1 mole
So-
buffer.
In plus 1 equals out. In plus 1 equals out. But what about this?
Mole buffer. Modular buffer.
Oh, so if we add n plus 1 mod buffer size is going to be equal to out. Because n here is 2. So 2 plus 1 mod 3 is going to be 0. And that's going to be out. So if we do the incrementation of, if we add 1 to n in a circular manner, it will be equal to out in all three cases. So the condition for full is this: n plus 1 mod buffer size equals out. Okay? So now, if we go through this, so this is the code that implements the bounded buffer problem. So we are creating a structure that has a buffer in it. The buffer is just an array. And we have these in and out that are initialized to 0, as we did here. Then, on the producer side, the producer will wait when the buffer is full. And the condition for full is n plus 1 mod buffer size equals out. So here the consumer is going to be in a busy waiting loop. As long as this condition is true, the producer is waiting, so it will keep looping. When this condition becomes false, the producer will proceed and produce the next item, then it will increment in a circular manner. Okay? So now, in this solution, the producer is in a busy waiting loop. So we call this busy waiting, because the producer is continuously checking on this condition. We will see more efficient ways of making a process wait in chapter 5. So chapter 5, basically we will be looking into more advanced ways of synchronizing the producer and the consumer without wasting CPU cycles. So this is, the producer here is wasting tons of CPU cycles waiting for this condition to become false. Okay. Now on the consumer side, the consumer will wait when the buffer is empty, and the condition for empty is n equals out. So this is the condition for empty. Then it will put the next item in the buffer, and it will increment out in a circular manner. Okay? Questions on this? Questions? Okay. So now, how do we create a shared memory buffer using the POSIX API? So there are 3 APIs that we use to create a shared memory buffer. There is shared memory open, which creates a shared memory buffer, and you give it a name. You give it a name, and there are some flags. The flags that what we are interested in are these: create and read write. So this flag indicates that this is the creation of the buffer. So this process is creating the buffer. So here it means create it if it doesn't exist. And read write means that this process can read and write, both read and write. So we are opening, we're creating a buffer. This is truncation. Truncate, if truncate just sets the size of the buffer. So we're setting the size of the buffer to 4K here. Then the third API maps that buffer into a pointer into the address space of the process that that did the shared memory open. So this map, to the map you pass the file descriptor. So there is a shared memory file descriptor that gets returned by this API. This is what you pass to ftruncate, and this is what you pass to map. And so this is saying, okay, map 4K of this buffer into this pointer, and this is the file descriptor, and this is, I need this buffer to be writable. Okay. In fact, we will look into more details when we look at the code for assignment number 1. But let's now go through this example. This is a very simple example for a producer that produces hello world. So this producer produces hello world. The producer in assignment number 1 will produce random numbers. So it just it creates a couple of strings. Now it does the shared memory open to create a shared memory buffer. And it sets the size to a certain size. Then it does the mapping, and it maps it to a certain pointer in the address space in the of the process that is creating this. Then once you get this pointer is going to be a void pointer. It's a void star of type void star, which means that it's a generic pointer that you can typecast it to anything. So here you can just treat that pointer as an array. And here it's being treated as an array of strings. Sorry, not an array of strings, an array of characters, which is a string. And the process is writing a couple of strings in it. Okay, so in the assignment, we will not be doing strings, we will be doing integers. So the producer will be producing integers, not strings. And our consumer will be reading numbers, not strings. So here on the consumer side, it's doing the same thing. It's doing shared memory open, and it's doing the shared memory map, mapping that into a pointer. Now the question is, we want the producer and the consumer to map or to open and map the same shared memory object. So how are we telling the system here to open the same shared memory object that the producer created? So we need to tell the system to open the same shared memory object that the producer created. So how are we telling the system to do this?
File descriptor?
No, the file descriptor is not something that we are passing to the system. It's something that the system is returning to us. So the system is returning to us a file descriptor. So how do we make it? How do we tell it to map the same shared memory object? Well, it's this name. We use the same name. So in the assignment, the name of the shared memory object is going to be homework 1, your name. Okay. So if you use the same name on both the producer and the consumer, they're going to map to the same shared memory object. If not, then well, it's not going to do anything. In fact, if you don't add the create flag on the consumer side, and the consumer doesn't create. So here you are trying to open a shared memory object that does not exist. So this will fail. If you give it a different name, it's going to fail. Okay. Now here in this example, the consumer is going to be reading the strings. In assignment number 1, read only will not be enough. Our consumer will be modifying the buffer, not only reading it. Why? Because our buffer in assignment 1 is going to have a header. So this is the shared memory object. So we will have a header with 4 fields in it. So this is the header. And then we have the body of the buffer that has the items. So then you'll have the numbers. In the header, we have the buffer size, we have the item count, we have in and out. So these in and out indices are going to appear in the header. So now it should become obvious why we need, why the consumer must have the right to act, to modify, to write to the buffer. So why does the consumer need to write to the buffer in this case?
Change the out.
Yeah, exactly. So the answer is changing out. Because here, whenever the consumer consumes something, it needs to modify app. So if in the assignment we do this, we open with read only, it's not going to work. In fact, our consumer is not going to touch any of the values, so it's going to read everything. Everything will be read only, fine, except the out. This particular number will be modified by the consumer. Okay. So in fact, I will go through the assignment in more detail next time. But in the meantime, take a look at it and come prepared with questions. So next time we'll go through the assignment in greater detail.